All right, let's talk about the dot product of two vectors. Definition. Um, Now, consider the angle, let's call it theta, between two vectors. So if theta is the angle between the vectors u and v, let's do this. I'm going to fit it in here. Ooh. U and v. So what am I talking about? So I have this angle, or this vector. This is vector u, and this is vector v, and let this be theta. Okay, if this is the case, then the dot product of u and v is defined as u dot v, and is the magnitude of u times the magnitude of v times cosine theta. All right? So let's look at some special cases. Or let's look at different cases. So assuming, let's assume that theta is equal to 0. If this is the case, then u dot v is just equal to u, magnitude of u times magnitude of v times cosine of 0, right? Which is just 1, right? So if you have the two angles or the two vectors kind of almost parallel to each other, they're parallel to each other, I guess. So this is, that is, let's say v, and this is u. Then their dot product is just the product of the magnitudes of the two vectors. Now, how about if theta is between 0 and 2 pi? Sorry, 0 and pi over 2. Then the dot product is the magnitude of u times magnitude of v times cosine of theta. Magnitude of u and magnitude of v are positive numbers. They're always positive because they come out of the square root. They're the result of computing a square root. Now, cosine of theta in this case is going to be positive. So that means that this will always be positive, right? So if you have two vectors like this, let's say this is u, this is v, right? Then the dot product is always going to be greater than 0. Now let's look at another case. If theta is equal to pi over 2, what happens then? Then u dot v is going to be magnitude of u times magnitude of v times cosine of pi over 2. The cosine of pi over 2 is 0, so the dot product is going to be 0. So if you have two vectors like this, their dot product is always going to be 0. Okay. So we say that they are orthogonal to each other. So orthogonal. Okay. Now, if theta is between pi over 2 and pi, I want you to check that the u dot v is going to be less than 0. So if you have two vectors like this, two vectors, the magnitude is always going to be less than 0. And lastly, let's look at the last case. If theta is equal to pi, then u dot v is going to be negative magnitude of u times negative magnitude of u times magnitude of v. So having known why the first case holds, explaining to yourself why this one holds should be easy. All right. Now, if you look at this formulation, that the dot product of u and v is magnitude of u times magnitude of v times cosine of theta, it's quite easy for us to calculate magnitude of u and calculate magnitude of v, but calculating cosine of theta can be difficult if we don't know the angle between them. It's easier if we know that the angle, if we know that the two vectors are orthogonal or something like that. But if we don't know, then it's going to always be difficult for us. But let's not worry. There is a theorem that teaches us how to compute the dot product without having to deal with the angle between them. So this is a theorem, all right, for computing the dot product. Okay. So if we let u be u1, u2, u3, and let v be v1, v2, v3, then u dot v, this will be the easiest thing you will learn in this course. U dot v is simply u1 times u1 times v1 plus u2 times v2 plus u3 times v3. Okay. Very simple. Just multiply them component-wise and add the results. All right. Let's do one example. If we let A be 2, 2, negative 1, and let B, the vector B, be 5, negative 3, 2. Okay? Let's find the dot product A dot B. A dot B is equal to 2 times 5 plus 2 times negative 3. I hope you're following. Plus negative 1 times 2. So this is going to give us 2. I want you to check my answer. All right. The next part of the problem, we would like to find the angle between A and B. All right. Remember that the dot product of A and B is the magnitude of A times the magnitude of B times cosine of theta, and theta is the angle between them. So this implies that cosine of theta, the angle between them, is simply A dot B all over magnitude of A times magnitude of B. Okay? So we need to find the magnitude of A, which is square root of 2 squared plus 2 squared plus negative 1 squared. This should give us square root of 9, which is 3. Check my results. And the magnitude of b is the square root of 5 squared plus negative 3 squared plus 2 squared, which should give us square root of 38. All right, so we want the angle between them. We know that the cosine of the angle between the two vectors is going to be a dot b, which is 2. We found a dot b to be 2 from part A. Then all over 3, which is the magnitude of b, magnitude of a, times square root of 38, magnitude of b. So if you calculate the theta now, to calculate the theta is just to take the inverse cosine of 2 over 3 square root of 38. If you do this very well, you get 84 degrees. That's what I got. So, and I'm believing that my answer is right. All right. So you might be asking, why do we need a dot product? This example, the second part of the example, answers that question. The dot product can just be defined as a way of measuring the angle between two vectors, basically, right? Because if you look at the magnitude of the two vectors, if you think of them as just a constant, right? And then you look at cosine of theta. So that means constant times cosine of theta. So in other words, the dot product of two angles is a weighted version of the cosine of the angle between the two vectors, right? So in other words, you're just computing the angle between the two vectors, or the cosine of the angle, which is, in a way, is equivalent to the angle. All right, because if you know the cosine, you know the angle. Okay, we're going to look at something we call the orthogonal projection. All right, so I want you to consider this. Assuming you have this angle or this vector, and then you have another vector v, or you have another vector u. This is v, and this is u. Now, assuming that the vector u casts a shadow on v, or its shadow is on v. So think about it that way. So we look at this as the projection of u onto v. Okay. Now there's an angle between them. Okay. Now, so the orthogonal projection, I love that word, even though I suck at pronouncing it. The orthogonal projection of u onto v is the shadow of u on v, and is denoted projection u v. So that's the notation. Now the scalar component of u in the direction of v is the length of this so-called shadow. And this scalar component is denoted uv. All right, so put this in a box. Put this in a box. I don't know why I'm doing that, but it just looks better that way. All right. Let's figure out how to calculate this. Let's make some argument. The length of this shadow, the length of the green shadow, length of the projection. If you look at it, assuming you complete this right angle triangle, since this projection is on the adjacent, then the length, let's call it the length of projection, it's simply u, magnitude of u, times cosine of theta. Magnitude of u times cosine of theta, because u is, magnitude of u is the hypotenuse. Now, we can think of the unit vector, parallel to the projection is, let's see, or let's look at the unit vector, the unit vector in the direction of v. This unit vector is simply v over the magnitude of v, right? Therefore, the vector, the orthogonal projection, which is that vector, remember, any vector in the direction of v that's parallel to v is just a scalar multiple of the unit vector in the direction of v, all right? So what we can now say is that the length is u, a magnitude of u cosine of theta. So we can do this projection of u onto v as magnitude of u cosine of theta times v over magnitude of v. Therefore, and the scalar projection, which is just the length we already got, is of u and v, is just magnitude of u cosine of theta. Now let's observe a few things. Let's observe one thing. U, v, scalar of u onto v is the magnitude of u. The cosine of theta, if you look at the definition of the dot product, then cosine of theta is just u dot v all over magnitude of u times magnitude of v. So all this can be simplified as u dot v over magnitude of v. All right. And now let's also observe again that the projection of u onto v is now magnitude of u times u dot v over magnitude of u times magnitude of v, right? So that's our, this is just magnitude of u times cosine, right? Times cosine of theta. That's all. All right. Then we're going to multiply it by v over magnitude of v. So this is going to be u dot v over v dot v times v, because v is a vector. So I just want to point out that v here, u and v are vectors and their magnitude are scalars, okay? So why is this, what did I do here? How did I end up with these results? I canceled this, right? And then this and that will cancel out, right? Now it's left for you to prove that I want you to show or to think of why, the reason why magnitude of V times magnitude of V is equal to V dot V. Okay? So what did I do? Let's put arrows on top of all our vectors. So this is to make it clearer. Okay? All right. Okay. So in summary, projection of U onto V is U dot V over V dot V times U. Times V. In terms of the dot product. All right. So, and then the scalar version, scalar component of U, V, is U dot V over magnitude of V. Okay. Let's do some examples. Let's do an example. Let's call it example 2. Let U be 4, 1 and V be 3, 4. Mind you, we are kind of going back to vectors in a plane, which is fine. Let's find a projection of U onto V. So the projection of U onto V, let's rewrite the formula. Projection of U onto V is just going to be U dot V, right, over V dot V. All right, times V. Okay, so this is going to be U dot V is 3 times 4, or 4 times 3, plus 1 times 4, all over V dot V is 3 times 3 plus 4 times 4. And then we're going to multiply it by V. V is 3, 4. Okay. So this is going to end up being 16 over 25, 3, 4. Okay. So that's the projection. The projection is always going to be a vector. All right, so this vector is actually 48. 48 over 25, 64 over 25. Always going to be a vector. However, the scalar component is always going to be a scalar. Projection is a vector. Scalar component is a scalar. All right, so let's find the scalar component of what we just did, U, V. So U, this is going to be U dot V over magnitude of V, which is just 16 all over 5. Okay, all right. All right, so we can actually maybe make a diagram of this and see and try to explain to ourselves further geometrically how this worked. So if we look at, let's see. All right. So this is 1, 2, 3, 4. And then 1, 2, 3, 4. So U is 4, 1. 4, 1. So let's make 4, 1. should be here. No, 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 it's not there. This is 4, 1. And then V is 3, 4. So this is 4 is here. 1 is there. V is 3, 4. 3 and 4. Let's go with a lighter color. No, maybe, yeah, let's go with a lighter color. 3, 4 over here. So this is V and this is U. Now the projection, so if you project this if you project U onto V, you want orthogonal projection, meaning that you're supposed to get a right angle triangle there, or a right angle triangle when you complete it. So the orthogonal projection, let's make it red. So we get this. Okay, so the orthogonal projection 24 over 25, 48 over 25, and 64 over 25. So approximately it's supposed to be around here, around 2, you know, and then it's supposed to be there. 64 over 25. So let's see. Let's look at these fractions, convert them to decimal, and make sure that my diagrams are okay. My diagram is not to scale, so it's going to be a little bit out of whack. So, but let's see. 48 over 25. 1.92. So, but we're kind of off. 1.92. Even though 1.92 is supposed to be there. So approximately, it's fine. And then 64 over 25. 2.56. Okay. Something is wrong. 2.56. Well, let's do it again. I want to try this again, make it more what do I call it? More to scale. Let's make it more to scale. So to do that, I'm going to change the paper. Use a smaller paper. Maybe this. Right? 1, 2, 3, 4. Okay. So let's do this. That, and then that. Okay, so 4, 1, 1, 2, 3, 4, 1. So this is just our U, the green vector. This is U, and then V is 3, 4. 3, 4. 1, 2, 3, 4. All right, and then 3 and 4. Let's use blue. Okay. All right. So let's look at the orthogonal projection. Orthogonal projection. Let's say it's red. Okay. Okay. I want to make it more, a little bit more orthogonal. All right. Okay. So this is more like it. Okay. So 48 over 25. Let's see. I'm trying it on my calculator, so I'm not a genius. 48 over 25 is 1.92. 1.92. And then 64 over 25. 2.56. All right. So this makes sense. This is 1.92 here. And this is 2.56. All right. So that's how projection works. So when you project V, we projected U onto V, and we got another vector. And geometrically, we got the correct result that we got when we did it with algebra. So we should be happy. All right, we're going to stop here. When we meet the next time, we're going to talk about work. Maybe we're just going to talk about it in class, but I want you to look it up. Look up the examples on work. Look at the work application. This is for you. So read up the work applications of the dot product. Work, an application of dot product. Of the dot product. And I think, let me see, what page is this in the book? The book we use it. All right. Okay, so this is on page 832. Page 832. And the book we're using is Calculus, Early Transcendental, and this is by Briggs, Cochrane, Gillett, and Schultz. All right.